Urine formation is the topic of this screencast, which may be found in Chapter 15 of your textbook. The objectives of the screencast are as follows. Explain the process of filtration. Explain the process of reabsorption. Explain the process of secretion. Describe the normal characteristics of urine. List substances normally found in urine. List substances that when found in urine may indicate disease. Urine is formed by the kidney from blood. So all the components of urine originally came from the blood. Let's take a moment to review the components of whole blood. Red blood cells represent 44% of blood. White blood cells and platelets contribute another 1%, and the remaining 55% of whole blood is plasma. And plasma is 90% water, and the other 10% are the solutes contained in plasma, such as nutrients, glucose, amino acids, ions, hormones, respiratory gases, nitrogenous waste products. All of those substances are carried in the plasma portion of blood. It is no coincidence that plasma and a typical sample of urine are very similar in color, as it is the plasma portion of blood that will be used to form urine. We will start our discussion on urine formation by first outlining the three processes of urine formation, just as we did in the previous screencast. And as we did in the previous screencast, we will use this schematic of the nephron, which is shown in your book. This portion of the diagram represents the renal corpuscle. Recall that the renal corpuscle includes the glomerular capillaries as well as the glomerular capsule. As blood passes through the glomerular capillaries, water and solutes that are smaller than large proteins are forced through the walls of the glomerular capillaries, and they enter the glomerular capsule. Basically, the plasma portion of blood minus the plasma proteins are able to cross the capillary walls and enter the glomerular capsule. So the filtrate, as it's now called, that's formed in the glomerular capsule is basically the plasma portion of blood minus the plasma proteins. The red blood cells, the white blood cells, and the platelets are too large to cross the capillary walls. This process is called filtration, and it is occurring in this schematic at location small a. This filtrate then passes into the renal tubule, and the renal tubule is represented here collectively as the proximal convoluted tubule, the loop of Henle, and the distal convoluted tubule. Now, let's consider this filtrate for a moment. So this filtrate contains waste products, yes, but it also contains nutrients that the body needs, such as glucose and amino acids and lots of ions. And so here, reabsorption is going to occur as substances that are needed by the body are going to be transported from the renal tubule back into the blood specifically of the peritubular capillaries. And this is called reabsorption, not absorption, but reabsorption, as the body is reclaiming or reabsorbing those substances that are needed that were filtered from the blood. And this is occurring on our schematic at location small b. In addition to reabsorbing substances that are needed by the body, there are still substances in the blood that the body does not need that are going to be transported from the blood of the peritubular capillaries into the renal tubule. And this is occurring at location small letter c, and this process is called secretion. It's basically reabsorption in reverse as substances are transported from the blood of the peritubular capillaries into the renal tubule. substances that the body does not need, such as drugs that have been broken down by the body, excess ions such as hydrogen ions, potassium ions, and waste products such as creatinine are secreted from the peritubular capillaries into the renal tubule. After those three processes of filtration, reabsorption, and secretion, what remains is urine, typically low in nutrients needed by the body and high in nitrogenous waste products and ions that are in excess in the body, or ions that the body does not need. So those are the three processes involved in urine formation. We will now consider each process in detail. First, let's consider the process of filtration, which occurs in the renal corpuscle of the nephron. Filtration is a passive process as water and solutes move from high pressure in the glomerular capillaries to the lower pressure found in the glomerular capsule. So water and solutes smaller than proteins are forced through the capillary walls and into the glomerular capsule. So this is a schematic I drew that illustrates what's occurring across the glomerular capillaries. The capillary bed is fed by a larger afferent arteriole shown on the left, and a smaller efferent arteriole is draining the capillary bed shown on the right. The smaller width of the efferent arteriole maintains pressure across the glomerular capillaries, and any substances that are small enough to cross the capillary walls is able to pass into the glomerular capsule. Blood cells and plasma proteins are too large to cross the walls of the capillaries, so they do not pass into the glomerular capsule. So the filtrate that is formed in the glomerular capsule is basically the plasma portion of blood minus the plasma proteins. The filtrate then passes from the glomerular capsule into the proximal convoluted tubule. So filtration has occurred in the renal corpuscle, and the filtrate will now pass into the renal tubule. There, the second process of urine formation will occur, reabsorption. During reabsorption, substances are transported from the renal tubule into the peritubular capillaries. The peritubular capillaries arise from the efferent arteriole, and they end with an attachment to a venule. The peritubular capillaries are more typical of capillaries in that the blood in the peritubular capillaries is at low pressure. Notice that the peritubular capillaries cling very close or tightly to the renal tubule for almost its entire length. This will allow the peritubular capillaries to reabsorb or reclaim those substances which are needed by the body. Substances that the body needs and that we don't want to lose through the urine are now going to be reabsorbed. Substances like water, a great deal of water is going to be reabsorbed to prevent dehydration, and nutrients like glucose, amino acids, as well as many different ions that the body needs will be reabsorbed. Waste products, substances that the body has no use for, or that if they are allowed to build up to high enough concentrations can cause toxic effects, these waste products are poorly reabsorbed. These include urea, which is a nitrogenous waste product of amino acids, uric acids, which are nitrogenous waste products of nucleic acid metabolism, and creatinine. Creatinine is a waste product of creatine phosphate metabolism. Now that the nephrons have reabsorbed those nutrients that the body needs, there are still other substances that were never filtered from the blood and are still there. By the process of secretion, these substances will be transported from the blood of the peritubular capillaries into the renal tubule. Secretion is basically reabsorption in reverse. Substances are transported from the peritubular capillaries and into the renal tubule. Substances such as drugs. Many drugs are cleared from the blood by secretion. Anyone who has taken penicillin has experienced this, as the urine typically takes on a sort of moldy, musty smell. The body is so good at clearing penicillin and other drugs from the blood that you typically have to take several doses daily. Also, you inadvertently consume small amounts of potentially poisonous substances in the water you drink and also in the food that you consume. And many of these potential toxins get into the blood and are cleared from the blood by secretion. And of course, there are ions that are in excess in the blood that are also secreted into the renal tubules. Now let's take a closer look at reabsorption and secretion using this figure of the nephron from your book. Here we have the renal corpuscle where filtration occurs, the proximal convoluted tubule, the loop of Henle, and finally the distal convoluted tubule. You may ask, so where are the peritubular capillaries? Well, it's sort of understood that they are winding around the entire length of the renal tubule, but to include them would make for a pretty messy figure and not a very useful figure at that. So it's sort of understood that they're there, although not shown. So an arrow pointing away from the renal tubule is understood to be pointing toward the peritubular capillaries and would represent reabsorption. An arrow pointing toward the renal tubule would be understood to be pointing away from the peritubular capillaries and therefore representing secretion. Now to the details. Filtrate is formed in the glomerular capsule and moves into the proximal convoluted tubule. In the proximal convoluted tubule, this is where most reabsorption and most secretion occurs. 100% of glucose, amino acids, and other organic nutrients are reabsorbed here, and most ions such as sodium and chloride and bicarbonate are reabsorbed here as well. Most secretion of poisons and excess ions, such as hydrogen ions, occurs here as well. The remaining filtrate then moves into the loop of Henle. In the loop of Henle, we don't have any secretion, but we do have reabsorption of water and also of some ions, such as sodium and chloride, some magnesium, and a few others. Moving into the distal tubule, we again have reabsorption of ions such as sodium and chloride. We don't have as much reabsorption as occurred in the proximal convoluted tubule, but there is some. And we also have some secretion of poisons, metabolized drugs, and excessive ions. Again, let me stress that most reabsorption and secretion occurred in the proximal convoluted tubule. The amount occurring in the distal convoluted tubule is small in comparison. The contents of the renal tubule then moves into the collecting duct, and along the entire length of the collecting duct, we mainly have reabsorption of water and sodium and chloride, such that what leaves the collecting duct we call urine, and it consists mainly of water with nitrogenous wastes, metabolized drugs and poisons, and other unneeded substances. So to quickly summarize urine formation in brief, filtration occurred in the glomerular corpuscle, where the plasma portion of blood minus the plasma proteins moved into the glomerular capsule. What is now known as filtrate passed into the renal tubule, where reabsorption allowed the nephron to recapture or reclaim nutrients and substances needed by the body, secrete into the renal tubule substances not needed by the body or substances that were in excess, and what remained after those three processes was what we call urine. Now that you have a basic understanding of how urine is formed, let's look at the normal characteristics of urine. In terms of solutes typically found in urine, ions such as sodium, potassium, bicarbonate, as well as other ions are normally found in urine. The exact concentrations and composition of ions really depends on a lot of factors, including the person's diet, if they're taking any dietary supplements or mineral or vitamin supplements, etc. Nitrogenous waste products, of course, you'd expect to find in urine, including urea, uric acid, creatinine, as well as ammonia. And of course, breakdown products of drugs and poisons and toxins, as well as other substances that the body needs very little of or perhaps has no real use for. You would expect to find those in urine as well. Urine should normally be sterile with no microorganisms present. This is because blood should typically be sterile, and as urine is made from blood, urine should be sterile as well. When you are asked to provide a urine sample for health monitoring purposes, you're always instructed to initiate urination first and then to capture the urine specimen. This is to ensure that any microorganisms on the surface of the opening of the urethra are sort of blasted away by the urine stream first prior to capturing the sample. Fresh urine typically has a slight smell to it. This can vary, of course, due to diet. Certain plants can change the smell as well as the color of urine considerably, and drugs can alter the smell of urine as well, as previously noted. Urine that sits around for a while can give off quite an unpleasant smell as bacteria begin to grow and metabolize the contents of urine. Urine is often a somewhat yellow color, and this is due to the presence of a substance called urochrome or urobilin. Urochrome is a byproduct of hemoglobin metabolism. As red blood cells are broken down by the body, the hemoglobin they contain is broken down as well, and one of the byproducts of that hemoglobin metabolism is urochrome. Urochrome passes into the blood, it's filtered by the kidneys, and becomes a component of urine. An individual's level of hydration can affect the color of urine. If a person is well hydrated, then the urine will tend to be dilute, the urochrome concentration will be lower, and the urine will be lighter in color or even colorless. On the other hand, if the person's not well hydrated or if they're dehydrated, the urochrome concentration will be high. This results in a darker colored urine, particularly if the person is dehydrated. This figure I obtained from Nurse Buff Urine.com illustrates the range of urine color that can result from different levels of hydration. Now, I wouldn't put a lot of stock in the recommendations that are listed by each shade, but in general, just understand that the more hydrated you are, the lighter your urine will be, and the less hydrated you are, the darker your urine will be. Your diet can also alter the color of your urine, especially specific vegetables. Another indication of hydration is the specific gravity of urine. Specific gravity is a measure of solute concentration. Typically, the specific gravity of urine is greater than that of distilled water. Distilled water, of course, is essentially pure water and would have a specific gravity of 1.000. Urine typically is greater than the specific gravity of distilled water because it's water with some solutes dissolved in it. A concentrated urine would have a higher specific gravity. If we were dehydrated or just waking from 6, 7, 8 hours of sleep, you would have a more concentrated urine. It would be darker in color and it would have a higher specific gravity. On the other hand, if you were consuming large amounts of fluids, you would be well hydrated, you would have a lighter colored urine, and your urine would also have a lower specific gravity. It would be closer to the specific gravity of distilled water. The pH of urine is typically around 6. However, there are a lot of factors that can affect the pH of urine, and it can vary significantly. Foods and dietary supplements can alter pH. Someone who has a lot of meat and dairy products in their diet will tend to have a more acidic urine, while vegetarians and vegans especially will tend to have a more alkaline urine. Now that we have discussed the normal characteristics of urine, including the substances normally found in urine, let's consider for a moment substances that are not normally found in urine. Glucose, although filtered from the blood, is normally completely reabsorbed from the proximal convoluted tubule. Therefore, we would not normally expect glucose to be found in the urine. Glucose in the urine may indicate an excessive consumption of simple sugars or diabetes mellitus. Blood proteins, other large proteins, red blood cells, white blood cells, hemoglobin, that if you recall is a protein, all of these substances are too large to be filtered from the blood, and therefore you would not expect them to be found in urine. Lastly, bile, which is produced by the liver, secreted into the hepatic ducts and then the bile duct, stored in the gallbladder, and eventually secreted into the duodenum, would also not be expected to make its way into the urine. If it does, then one would expect, or suspect rather, some type of liver disease such as hepatitis. This figure in your book provides possible causes for the presence of these substances in your urine. However, I am not holding you responsible for knowing these causes, just the fact that these substances are not normally found in urine. Now let's review the objectives of this screencast. Explain the process of filtration. Explain the process of reabsorption. Explain the process of secretion. Describe the normal characteristics of urine. List substances normally found in urine. List substances that when found in urine may indicate disease. The topic of our next screencast will be urine storage and micturition.